Welcome to this explainer. Okay, let's just dive right into this and uncover exactly why so many AI pipelines are breaking and why Apache Airflow is literally the exact tool data engineers need to fix them. If you've been working with data pipelines for any length of time, you know the drill. Data usually shows up in predictable patterns, right? We define the order of tasks, we schedule them, we track them, boom, done. But then comes agentic AI, and it has completely disrupted that predictable, comfortable execution paradigm. We're seeing this massive shift where data and AI need to live within the exact same pipeline. And suddenly, our old, reliable orchestration methods, yeah, they're being put to the absolute ultimate test.
So why do so many AI pipelines silently fail or just rack up massive LLM costs in production? Well, we're going to explore the total chaos that happens when unbounded large language model reasoning loops just run out of control. I mean, think about what an AI agent actually is for a second. Simply put, it gets some context, it calls a model, and then it just lets that model decide on its own which tool to call next, whether to execute it, and then it feeds the results right back into itself. It repeats this process over and over until some condition is met. And the crazy part? The number of iterations is often totally unbounded until the model itself decides, okay, I'm done. When you throw that kind of unpredictable, looping black box process into production without strict oversight, honestly, silent failures and skyrocketed cloud bills are practically guaranteed.
And this brilliantly illustrates the core problem. We're looking at a massive architectural conflict. See, standard Airflow DAGs have a fixed shape at parse time, but an AI agent, it decides its sequence of tool calls dynamically at runtime. In standard ETL, your tasks communicate nicely, schedules run on predictable heartbeat cycles, it's all very neat. But agent orchestration, the sequence of tool calls isn't even known when you compile your code. There's no way. And on top of that, standard communication methods, like XComs, they just weren't originally designed for an unbounded, unpredictable loop of intermediate AI tool results. It's a fundamental clash between rigid predictability and dynamic reasoning.
All right, Section 1, the solution. Let's look at how we actually fix this. To bridge this massive gap between unpredictable AI and structured orchestration, it turns out we don't actually need to throw away our existing orchestrators. Thank goodness. The real magic weapon here is the official Apache Airflow Provider's Common AI package. This introduces the agent operator to handle all those runtime decisions without altering the DAG's core meaning. And this is huge because it shifts the entire conversation from can Airflow schedule AI workloads to how can I optimally use it for AI. This Common AI package keeps the conversation history and those intermediate tool results living right in the same in-process run. It brings toolsets directly into the package. By leveraging this, you get to keep all the rock-solid reliability of your orchestration while empowering the AI to act dynamically within a safe, explicitly defined space. So, what makes this actually work at scale? It comes down to two crucial mechanics: dynamic task mapping for agent fanouts and deferrable operators. Look, agents usually work like a multi-step black box. If an agent has, say, 5 tasks and one of them fails, you definitely don't want the entire agent rerunning from scratch, right? That's just a waste. Dynamic task mapping allows a task to fan out into multiple subtasks. So if one subtask fails, the retry only applies to that specific piece. That gives you massive transparency and saves so much execution time. Plus, deferrable operators are just a massive blessing. When you're waiting for a long-running AI tool call or maybe a human-in-the-loop approval, there is absolutely no need for your worker node to hold onto that slot. It frees up resources, which is a huge advantage when you're scaling up. Now, let's talk about durable step-level caching, because the financial impact here is absolutely massive. Simply by setting the durable field to true, you cache your large language model responses. This ensures you never, ever pay for the same expensive generation twice on a retry. Imagine this. Your pipeline is almost finished. It's been running for a while, but the very last step fails. The worst. Without caching, a retry means executing all those expensive, time-consuming LLM calls all over again. But by just setting durable to true and pointing to an object storage backend, like S3 for example, Airflow retrieves the successful data from the cache and only makes the absolute necessary calls at the exact step where the failure occurred. And the best part, once the task succeeds, the cache auto-cleans itself. It's just a brilliant, brilliant cost-saving pattern. Okay, moving on to Section 2, orchestrating real-world AI patterns. Let's dive into some practical examples. Let's look at a real-world scenario here. Imagine a data team running a nightly job. The goal? Extract order data, summarize it, and catch any errors before the stakeholders ever even see it. This step-by-step flow shows exactly how we can use a large language model to check for schema drift, route logic based on those changes, translate natural language to SQL, and then finally analyze the report. Through a series of specialized decorators, Airflow is managing the entire sequence. We can literally ask the system, hey, was there a schema change? Is it safe to proceed, or did we miss anything suspicious? And it's all orchestrated seamlessly. We're moving way beyond just theoretical setups here. We're looking at how to prevent silent data corruption from ever reaching a critical board deck.
So, checking out task.llm schema compare versus task.llm branch. First, we outsource that schema drift detection to an LLM using the schema compare decorator. This then immediately feeds into branching logic driven by the model's safety assessment. By using that schema compare decorator, we're passing the complete schema definitions of our source and warehouse tables straight to the model. It analyzes them, reports back, easy. Then the branch decorator takes over. We give it a system prompt, asking if the nightly ETL is actually safe to run. And here's where dynamic routing really shines. If there are no critical mismatches, boom, it routes directly to our query generation step to write the SQL. But if something is broken, it branches off, halts the ETL, and pings the data team over on Slack.
Now, when that task.llm decorator generates the daily summary, we have got to implement strict usage limits and guardrails. We're talking things like limiting requests to, say, 5, and capping input and output tokens. Why? To prevent the large language model from spiraling into an unbound loop. This is an absolute necessity for production workloads, guys. By defining a usage limits object right inside the task, if the model hallucinates or gets stuck and tries to exceed 5 requests or hit our token limits, the task simply fails. Hard stop. That hard boundary is exactly what protects your system from catastrophic billing surprises while you're generating those stakeholder digests. And of course, we have to talk about human in the loop, or HITL. This is the ultimate safety net. Airflow acts as this vital checkpoint, using approval gates or iterative reviews to guarantee that, frankly, AI slop never reaches a board deck. You really cannot stress human in the loop enough. Think about it. When you're analyzing a final report for revenue anomalies, the output can be routed to an agent for further investigation. But before anyone acts on it, you institute an approval gate. A human actually has to look at it and approve, reject, or modify the output. Or you could use an iterative review. This gives the human reviewer, say, 5 chances to request slight modifications from the agent before finalizing the whole thing. It keeps humans firmly in the driver's seat. Let's look at some more advanced safety and retry tools. We have hook tool sets that restrict the LLM to an explicit allow list of actions. This is crucial for preventing accidental data deletion. And we pair that with intelligent LLM retry policies that actually let the model decide whether an exception requires a simple delay or a hard fail. I mean, imagine giving an AI agent access to Airflow's 350 plus hooks. Yikes. But by using a hook toolset, you explicitly define the allowed methods. Because you didn't specify delete, you can sleep soundly knowing the agent cannot wipe your database. And with those LLM retry policies, instead of just a dumb blanket rule, the LLM evaluates the error itself. If it hits a rate limit, okay, it triggers an exponential backoff. But if it hits a permission error, it knows retrying is pointless and it safely fails the task. So smart. All right, moving into Section 3, the future of MLOps. Let's see where this is all heading. Because orchestrating AI isn't just about execution, right? It's really about maintaining flexibility and visibility as this entire ecosystem just rapidly evolves. You get incredible portability via Pydantic AI connections. This allows you to swap your large language model provider by simply updating a string. You completely avoid having to rewrite your DAGs. If you looked closely at the code examples in our source material, you might have noticed there are actually no hard-coded models in the DAGs themselves. Nope. The Pydantic connection is defined purely with the provider:model string within Airflow's connection manager. So, if you suddenly need to switch from one model provider to another tomorrow, you just update that connection string and your pipeline just keeps running perfectly. Then, you add in observability and ecosystem bridges. We're talking open telemetry tracing out to Datadog or LangFuse, a native LangChain bridge, and MC connections. Put that all together, and you have unparalleled visibility into your AI workloads. Airflow just integrates so seamlessly with standard observability stacks. You can literally trace your agent's exact reasoning steps. And that MCP connection type? It even allows you to access MCP servers with streamable HTTP and standard I/O transfer types. It's deeply integrating your existing agentic frameworks right into the data orchestrator you're already using. I love this quote. Pydantic AI runs the reasoning loop. Airflow runs the schedule, the retries, the audit trail, and the human checkpoint.
Ultimately, Airflow is not trying to replace your agentic reasoning framework. That's not the goal. It's providing the desperately needed reliability and audit trail around it. This division of labor is precisely the point. Airflow isn't trying to be an agent. It steps in to handle all those heavy orchestration burdens, the SLAs, the caching, the complex branching, and of course that crucial human oversight. And it does all that so tools like Pydantic AI can just focus purely on the reasoning loop.
So if your AI workload is scheduled, batch, or async, why aren't you orchestrating it with the powerful tool you already own? To wrap up our explainer today, I really want you to consider this. For literally any non-conversational AI pipeline, the smartest architectural decision you can make is to leverage the robust orchestrator that is probably already sitting in your tech stack. Now, if your use case demands a sub-second conversational turnaround, okay, fair enough. Airflow's heartbeat cycle won't fit that latency budget. But for the massive growing category of agentic work that is scheduled, batch, or async tolerant, like those nightly checks, schema drift monitoring, and anomaly investigations, Airflow is undeniably ready for it. It completely bridges the gap between unpredictable AI and reliable data engineering. So I'll leave you with this. What hidden efficiencies could you unlock by bringing your AI workloads into the orchestrator you already trust?